implicit differentiation. So far we have considered function in terms of explicit function. Now we are now considering that is a case whereby y is written separately from x. Y is here, x is this explicit function. If they now say that implicit function, if both x and y are together, they will say that it is an implicit function. Now we define an implicit function as this. A function is said to be implicit if it is of this form. That is, function of x and y together is equating to 0. So we say that is an implicit function. For instance, x squared y squared plus 3 is equal to 0 is an implicit function. X squared plus 3y is equal to 5 is an implicit function. Now, how do we differentiate implicit function? Implicit differentiation is just like the normal differentiation that we have been dealing with. It's just that under normal differentiation, when we differentiate x cubed, you say that your answer is 3x squared. But under implicit differentiation, when you are differentiating y cubed, you also say that it is 3y squared. But since you are differentiating with respect to y, then you put the y dx there. That is how to differentiate implicit. For instance, if I want to differentiate cos y, I know that if I differentiate cos y, I will get minus sin y. Then, since I'm differentiating with respect to y, I will put the y ds. So let's take example. Example 1. I have this as an example. If I differentiate x cubed, I'm going to have 3x squared. I will leave that like that. If I want to differentiate y cubed, it will still be 3y squared. But because I am differentiating with respect to y, I'll put the y dx. That is that about that. Plus, I will differentiate 4x. That will give me 4. But if I differentiate 2y, it will give me 2. But because I'm differentiating with respect to y, I'll put the y dx. If I differentiate this one, I will get 0. After you have done this, you look for the common ones. You retain the common ones. You take the ones that are not common. You take them to the other side, so that we are going to have. So yeah, this is 3x squared. These are 4 equal to. I've taken minus 2 dy dx to the other side, and this is our plus 3y squared to the other side. That gives me, it will give me minus 3y squared. From this place, you make the y dx a formula by first factorizing. The y dx is common. That will be 2 minus 3y squared. Then finally, our dy dx that we are looking for will now be equal to 3x squared plus 4 over 2 minus 3y squared. So this is our dy dx. This is the differentiation of this implicit function. Now let's consider another example. This is another one. 2y cubed minus this is equal to this. I will differentiate this. If I differentiate this, normally I will have 6y squared. But because I'm differentiating with y, I will put the y dx minus. If I differentiate this, I will have 6s plus. If I differentiate 5y, I will have ordinary 5. Because I'm differentiating with respect to y, I will have the y dx. If I differentiate 7, which is a constant, I will get 0. From this place, you retain the one with the y dx, and the one without the y dx, we take it to the other side, so that we are going to have this. Now, the y dx is common. So bring it out, so factorize, so that we have 6y squared plus 5 equal to this. Finally, if you make the y dx 0 formula, it will be this over this. Now, for this one, observe that there's a product function here. So in that case, we have to apply product rule. And product rule says u dv dx plus v du dx. That is, we take this. What that simply means is that we take this, we differentiate this, plus we now take this one, we differentiate this one. So in that case, I will first take x cubed. I will differentiate y squared. If I differentiate y squared, I will have 2y. Well, because I'm differentiating with respect to y, I will put the y dx. So I've taken this, I've differentiated this. I will now say plus, I will now take y squared. I will differentiate s cubed. That will be 3s squared. Minus, I am differentiating this 3s. That will give me 3. This is cos y. If I differentiate cos y, I will have minus sin y. So that will now become minus 5 sin y. But because I'm differentiating with respect to y, I'll put dy dx equal to, if I differentiate 2x, I'm going to have 2. So let us retain all the ones with dy dx here and the one without dy dx to the other side. So in this one, if I rewrite this, I will have 2s cubed y dy dx minus 5 sin y dy dx equal to 2. I will take this to the other side. If I take this one, I will have minus 3s squared y squared. And this one, if I take it, it will become plus 3. So after that, you factorize the y ds out, which is 2x cubed y minus 5 sin y equal to 2 minus 3s squared y squared plus 3. So making the y ds formula, we are going to have this 5 minus 3s squared y squared over this, because 2 plus 3 has given me 5. So this is our answer to this question. Now let's consider another example. Example is here, but you observe that this one is a chain rule. And if you remember how I explained the chain rule, this is, forget about what is inside. Take it as if you are differentiating something raised to power 4. And if you're differentiating anything raised to power 4, it will give you that thing 4 times that thing raised to power 3. Then I'll say that times, I cannot differentiate what is inside. What is inside here? I will differentiate x. If I differentiate x, I will have 1 minus. If I differentiate 2y, I will have 2. But because I'm differentiating with respect to y, I will put the y dx. Now, this one is product rule. So I will use u dv ds plus v du ds. That is, I will take this, I will differentiate this. So if I take x, I will differentiate y squared. That will become 2y dy ds plus, I will not take y squared, I will differentiate x. That if I differentiate x, I will get 1. So from this place, I will just find a way of making the y ds formula. And if I expand this, I'm going to have 2y raised to power 3 minus 8 into s minus 2y raised to power 3 dy dx is equal to, this one is 2xy dy dx plus y squared. So from this place now, we just need to collect the like terms. The one with the y ds, take them together, and so that we are going to have, so and if I have, so we have the following. So I've rearranged it now. From this place, the y ds is common, so I brought it out, so it remains 2sy plus this. So finally, we make the y ds formula, and we are there. So that is that about the implicit differentiation. Let me show you some examples more that you can study on your own. So this is one example, and the solution is there. Another example with the solution. Another example with the solution, so you can study it. Now move to application of logarithm differentiation. So we recall that if y is equal to ln f of s, the y ds is f prime of s over f of s. That is, if you are given ln of a function, the differentiation is derivative of that function over that function. So that means if they now ask me to do this, to differentiate this, they want me to find, let's say example 1, find the y dx if y is equal to 8 raised to power x. If y is equal to 8 raised to power s, it's different from, assuming it is s raised to power 8, I would have said our answer is 8 s raised to power 7. But now what we are giving is s raised to power 8. In this type of case, we normally apply logarithm function. How do we start? We start by taking log of both sides. So that is, you put log here, you say ln y is equal to ln 8 raised to power s. Then by law of logarithm, this s will come to the back of it. It will become x ln 8. Now, after that, you differentiate both sides. If I differentiate both sides, I'm going to have, if I differentiate this ln, I'm going to have 1 over y. You know, normally if I differentiate ln x, I'm going to have 1 over s. Now, if I differentiate ln y, I'm going to have 1 over y. Then I'll put dy dx, as usual by implicit differentiation. Now, this ln 8 is a constant, so I'm differentiating only x. So if I differentiate this x, I'm going to have 1 ln 8. Then I'll make dy dx the subject of formula. If I make dy dx the subject of formula, this y will come and meet this. It will become y ln 8. But what's our y? Our y is 8 raised to power s. So our answer is 8 raised to power s ln 8. So that means if I differentiate y is equal to 8 raised to power s, then our dy dx is 8 raised to power s ln 8. I can generalize it like this. Generally, if y is equal to a raised to power s, where a is a constant, then dy dx is a raised to power s ln 8, ln a. That is, if this a is number raised to power x, then dy dx is this raised to power s ln a. That means if I'm asked to now differentiate this, something of this nature, 2 raised to power cos x, our dy dx, this is now share rule. I will just use this formula. If I differentiate 2 raised to power anything, it will give me 2 raised to power the same thing ln 2, just like what we have here. A raised to power s ln a to 2 raised to power cos s ln 2. But I will now say that times, I will now differentiate the cos itself. If I differentiate cos s, I will have minus sin s. So that my final answer is minus sin x dot 2 raised to power cos s ln 2. So that is the differentiation of y is equal to 2 raised to power s. Now considering a case whereby this is not a number, it's a variable, which is x, y raised to power s. We start by taking ln of both sides as usual. If you take ln of both sides, I'm going to have ln y here is equal to ln s raised to power s. Then by law of logarithm, this power will come to the back so that we have x ln x. After that, we now differentiate this ln y. If I differentiate ln y, I will have 1 over y dy dx equal to, this one now, ln s is a variable. This is also variable. In that case, it has become a product. So we apply product rule, which is u dv plus v du. That is, we take this, we differentiate this, plus we take this, we differentiate this. So if I take x, I'll differentiate ln s. If I differentiate ln s, I'm going to have 1 over s. Plus, if I take ln s, I'm going to differentiate x, which is 1. And our answer here will now be s cancel s, we have 1 plus ln x. If you make dy dx the same formula, this y will come here to become y times 1 plus ln x. But we have known what our y represents. It is s raised to power s into 1 plus ln x. So that means if I differentiate s raised to power s, I'm going to get s raised to power s into 1 plus ln s. Let's consider another example of this. Interesting one. Tan s raised to power sin s. Anytime you are seeing something like this, any form, just take ln of both sides. That will be ln sin, ln tan s raised to power sin x. And by then you apply law of logarithm. Bring this sin s backward. That is sin s ln tan s. Your own is now to know how to differentiate ln tan s. Because differentiating ln tan s, it will be differentiation of tan s over tan x. Now let me differentiate both sides. After you have done this, after you have applied the law of logarithm here, then differentiate both sides. If I differentiate this, I will have 1 over y dy dx equal to, this is product rule. I'll take sin s. I will differentiate ln tan s. And if I differentiate ln tan s, it will be differentiation of tan s, which is sec square x over, this is sec square x over tan x. So from this place, I have differentiated ln tan x. Plus, I'll take ln tan x. I'll differentiate sin s. If I differentiate sin s, I'm going to have cos s. So from that place, our y over y dy dx will now be equal to, if I expand this, I'm going to have sin s. Sec square simply means 1 over cos square s. Tan x simply means 1 over tan s simply means cos s over sin s, plus, let me bring cos s here, cos s ln tan s. Some things will cancel here. You observe, this is cancelled, this is cancelled. All we have left is 1 over cos s. So that if I make dy dx the same formula, it will be y times whatever we get here. So what we have left here is 1 over cos s, which is sec s, plus cos s ln tan x. But we have known our y. Our y is tan s raised to power sin s, then into sec s plus cos s ln tan s. So that solves this question. So you can be given anything. You can be asked to differentiate this. S raised to power sin s raised to power x, s raised to power y raised to power s, etc. Next one is differentiation of inverse trigonometric functions. These are inverse trigonometric functions: arc sin s, arc cos s, arc tan s, and so on. These are inverse trigonometric functions. Now the first one, I want to differentiate arc sin s. I can't differentiate it directly. What I will do is, let me say y is equal to arc sin s. Then I'll make s the same formula. If I make s the same formula, I'm going to have sin y. Because if I make s of arc sin s, arc sin will come here to become sin y. The next thing now is that I'm going to differentiate both sides. This has led to implicit differentiation. If I differentiate this, I will have 1 equal to, if I differentiate sin y, I will have cos y, then I'll put dy dx. If I make dy dx formula, dy dx is 1 over cos y. But let's recall, if you recall that cos y is cos theta is same thing as square root of 1 minus sin square theta. Therefore, our dy dx there will just be equal to square root of 1 minus, instead of cos y, I'll write it as square root of 1 minus sin square y. And that will be equal to 1 over square root of, our sin y here is x. So in that case, this will be 1 minus s squared. So that means if I differentiate arc sin x, my answer will be equal to 1 over square root of this. Similarly, if I follow the same thing and I want to differentiate arc cos x, if it is arc cos x, similarly, my answer will be equal to minus 1 over square root of 1 minus s squared. So you can try that, follow the same pattern, you get the same answer. Another one is number 3. We want to differentiate arc tan x. If you make x the same formula, it will become tan y. Then this has led to implicit differentiation. If I differentiate s, I will have 1. If I differentiate tan y, I will have sec square y, then dy dx. Making dy dx the formula, we have 1 over 1 plus sec square y. I will have 1 over sec square y alone. But we recall that sec square theta is same thing as 1 plus tan square theta under trigonometric identities. From that place, the y dx will now be 1 over, instead of sec square y, I'm going to have 1 plus tan squared y. But we have known our tan y here. Our tan y means x. In that case, here will now become x squared. So what we are now saying is that anytime I'm asked to differentiate arc tan x, my answer is equal to 1 over 1 plus x squared. So similarly, if I'm asked to differentiate arc cot s, my dy dx will be equal to minus 1 over 1 plus x squared. So this is the definition of arc cot s. For the next one, which is number 5, arc sec s, then s is equal to sec y. Then if I differentiate both sides, I will have 1 here. Here, if I differentiate sec y, I will have sec y tan y. I only need to recall that 1 plus tan square theta is equal to sec square theta. Sec square theta minus 1 is equal to tan square theta. So it will be useful for us there. Okay, there is dy dx here. Therefore, making dy dx a formula, I'm going to have 1 over sec y tan y. Then using the formula, if I make sec square theta the formula here, it will be okay. If I make okay, this is sec y already. Our sec y is x. So let me put x there. I don't need any representation for it. But there's tan y here. Tan y, if I make tan theta the formula here, it will be root of sec square y minus 1. We already know what sec means. Sec is our s. So in that case, our answer will just be s square root of s squared minus 1. So that means if I'm differentiating arc sec x, our dy dx will be this. Similarly, if I differentiate arc cosec s, our dy dx is minus 1 over s square root of s squared minus 1. So I want you to memorize all this, as will be useful for you in our subsequent solved problems. So we have the following as our table. If you memorize them again, I'll summarize the whole thing for you. If you differentiate arc sin s, you get this. If you differentiate arc cos s, you get this. Arc tan s, arc cot s, arc sec s, and arc cosec s. Now let's consider another question on this. See another question there. If y is equal to arc sin, tan s, the y dx is what? Now solution. This is chain rule. Our dy dx will be equal to, I'll just need to recall what arc sin means. So if I differentiate arc sin anything, I will get 1 over square root of 1 minus that thing squared. So in that case, if I differentiate arc sin tan s, I'm going to have 1 over square root of 1 minus tan squared x. Then I will say that times, I will now differentiate tan s. If I differentiate tan s, I will have sec square s. So that my final answer will become sec square s over square root of 1 minus tan squared x. So that is the solution to that. Now if I consider another example, let's say I have another example here, y equal to square root of arc sin s. I want to differentiate it. This is another chain rule. I would only need to, this is another chain rule. I'll use the shortcut to differentiate this. If I differentiate square root of anything, we know that it's always giving us 1 over 2 square root of the thing. That will say that times I cannot differentiate arc sin s itself. And if I differentiate arc sin s, I'm going to have 1 over square root of 1 minus s squared. So that my final answer will be equal to 1 over 2 square root of arc sin s into 1 minus s squared. So will be the solution to this. This is another example, and the solution is there. You can practice it. Solution is this is the solution. This question is there. The solution. Pause and practice. So this is another one there, and the solution. So the next thing now is we move to what we call differentiation of parametric equation. This is it. If a curve is of this nature, they will say that it's a parametric. How do we differentiate it? We use this formula. dy ds is equal to dy dt times dt ds. That's what we call parametric. Parametric equation differentiation. If s is equal to f of t and y is equal to g of t, dy ds is dy dt times dt ds. It sounds or looks like chain rule, but it's not chain rule. What we are saying is that if they say that parametric equation, if x is a function of a variable t and y is a function of another function of variable t, then that is when we have parametric equations. So and we use this formula to differentiate it. For example, now look at example. Find dy ds if y is equal to sine theta and s is equal to sine theta, cos theta. Now, for we to do it, we differentiate it, and we say dy d theta. If I differentiate this, I'm going to have, if I differentiate sine theta, I'm going to have cos theta. I'll differentiate this to ds d theta. If I differentiate this, I'm going to have minus sine theta. So our dy dx will now be equal to dy, the formula dy d theta times d theta ds. Although there's t there, but we are dealing with theta here. Dy d theta, that is cos theta, times d theta dt. Here it is d theta dx, but here what we have is ds d theta. In that case, our d theta dx we just interchange. This one is over 1 before, so it will now become 1 over sine theta. So our answer here is minus 1 over sine theta. So that my final answer is minus cos theta over sine theta. So that my answer is a minus cot theta. Let's consider another example for better understanding. S is equal to theta minus this, y is equal to this. Now, how do we differentiate this? I'll first find the s d theta. The s d theta is 1. If I differentiate theta, I will get 1 minus. If I differentiate cos 2 theta, I'm going to have minus 2 sine 2. That will become plus. The 2 will come out. That will be minus 2 sine 2 theta. And here I will have dy d theta. If I differentiate here, I will get 1 minus. If I differentiate sine 2 theta, I'm going to have 2 cos 2 theta. But in the formula, what I need is d theta dx. So d theta dx, this one is over 1. D theta dx is just interchange. 1 over 1 plus 2 sine 2 theta. From that place, our dy dx will now be equal to dy d theta times d theta dx. Our dy d theta is here 1 minus 2 cos 2 theta times d theta dx. These are the theta, there is division, so it's just over 1 plus 2 sine 2 theta. So that is the differentiation of the parametric equation. And if they say that second order derivative or differentiation, this is how we write it. D square y ds square. This is the same thing as d ds dy dx. This simply means I should differentiate dy dx. And if they say that second derivative, it means you should differentiate a certain function twice. For instance, if I'm having s cubed minus 5s squared plus 7, if I want to find second derivative, I will first find dy dx. This is 3s squared minus, if I differentiate this, I will have 10x plus, if I differentiate this, I will have 0. Second derivative simply means I should differentiate this one once again, and that will become 6x minus 10. So that is the meaning of second derivative. Even if it is third derivative, it will be written as this: the cube y dx cube. That is, I should differentiate second derivative, and that will become 6. So that is that about second derivative. You can apply it to any question. When you are given second derivative, it simply means you should differentiate the function twice. You first differentiate it once. Any answer you get, you differentiate the answer once again. That is the meaning of the square y dx square, or second derivative.